Okay, so I changed my mind. I'm going to go through this example because it's a classic circuit. Wheatstone bridge. It's a bridge circuit. So I've pre-drawn some of this because I want to give really good visuals for you to understand what's going on. So this circuit is neither strictly a series combination nor a parallel combination. It's kind of weird. And so we have to use Kirchhoff's rules to find the values of the target variables. So we're wanting to find the current in each resistor and the equivalent resistance of this whole circuit of 5 resistors. There are 5 unknown currents, but by applying the junction rule to junctions A and B, we can represent them in terms of 3 unknown currents, I1, I2, and I3. So let me draw where our equations are going to come from. So we're going to use our Kirchhoff loop rules, right? The sum of all the current, right? Equal to 0. And the sum of all voltage. I think it's this one that we're particularly using. Sum of all voltage is going to be equal to 0. So as we go around in a loop, we are summing the voltages. And so let me describe our loops. So the first loop we're going to consider is this one here, this path. Like that. And that's going to give us equation number 1. If we go along that, we have, so this is going to be equation 1, we have 13 volts, positive volts, from the EMF source, minus, right, V equals IR, and so we don't know what V is, but we know that we're looking for I, and we have R, so we'll go ahead and throw those in there. So I1, current through resistor 1 times 1 ohm, the value of that resistance of that resistor, and then also minus, and it's a minus because the voltage is dropping as it goes through that component. It's not a source of EMF, it's dropping, right? And then we have the current through the second one is I1 minus I3 here, times, again, 1 ohm resistor. And that must equal 0. Yeah? All right. The second loop that we're going to consider is outside the whole thing. So this loop. That's going to give us equation 2. So here we have, I will start after our EMFs, well, I'll start with the EMF source. We have 13 volts minus I2, here, times 1 ohm, minus, again, down here, I2 plus I3 times 2 ohms, and that must equal 0. So we skipped all of this junk here, right? All right. The third loop, right? We have 3 unknowns, I1, I2, and I3. So we need 3 equations. So the third loop that we can consider is this one in here. Yeah, that direction. Well, you can go either direction, but this is the one I've worked out. Like that, right? Or I'll say like that. And that is going to give our third equation. Okay. So 3. And this is kind of a weird one because it doesn't go around the whole circuit, right? It doesn't bring you back to that EMF source. So I'm going to write it down, and then I'm going to show you on the right what this path is kind of like. Yeah, what each path is kind of like, I guess. All right, so we have minus I1 times that 1 ohm minus I3 times that 1 ohm plus I2 times that 1 ohm. Okay, so I just said that voltage drops as you go through these resistors, right? And why is this now plus? And how is this loop going the opposite direction of the way that we've described current is going? Well, current doesn't actually have to follow these loops. We're just characterizing paths of elevation change on different looped segments of this circuit. So the first path is along the inside, and so we would start, if you look at my visual over here, start here, right, your little person, and then you go down this ramp from point C to point A to point D, and then back to the top. So you go C, A, and then, let's see, I need another I need another segment here, so then there's some other bit here that you go straight to D here. Boom. And that would be for R4. And this is R5. This is also R5. And this one got covered up. Oops. But this is R3. Okay. So if you were our dude here and you were going on loop number 1, you would have gone down from A to C, so you've gone down that ramp, and at each one of these connector things, you can transfer ramps, I guess. And I didn't, we can take a guess as to the steepness of the ramp. I haven't figured this problem yet. We haven't gotten to the end, so I'm ignoring the steepness of the ramp, but you can imagine each one of those might have a different amount of steepness. And so then we're going to transfer over to this ramp and then go down from point A straight down to point D. And then you would continue down here, the EMF elevator, and go back to the beginning. So that's 1. Path 2 is around the outside, the whole outside. So you start up here, and then you go from point C to point B. So you'd go down this ramp all the way to point B, and then from B to D. So you just keep going there, and then you take the EMF elevator up, and you can start again. And finally, what cool color shall I use? I think, that probably won't be that different, so this one. Yeah. Path 3 is this little loop, and that's the one that's a little bit weird. So you start at C, right? You start at C. So we'll put our guy here. The loop doesn't involve the elevator. You just poof to the top, right? And then we're going to go from C to A. So he's going to take this path here, right? And then from A to B, so then down this ramp to B, and then back up to C. So he climbs back up this ramp, right, to go back to his starting position. So he doesn't really complete the circuit, just as that loop doesn't go around the whole circuit. But that still works, you could still scramble back up that hill and you've reached that same original starting position. So path 3, that guy's just kind of a ninja warrior, and he just went right back up the ramp. So that's the way to think of it in terms of elevation change, potential differences, taking these different loops around the circuit. So now we have our 3 equations, 3 unknowns. You can imagine going and solving for each of those, and I'll let you finish that up, but the equivalent resistance of the whole dang thing is 1.2 ohms. What else should I give you to see if you confirm that you do it right? I1 is equal to 6 amps. I2 is equal to 5 amps, and I3 is equal to -1 amp. All right. So there we go. So the negative sign tells you that the direction on that path is actually the opposite direction than we first assumed. So this I3, we didn't know how it would work out, and we just thought, well, maybe it's going to the right. Depending on the arrangement, the resistances, the whatever, perhaps it's going to the left, and it's actually taking that path, right? And so that's what the negative sign tells us, is that actually it's traveling this way, right? Because we defined this way as positive, and it turned out negative, so it's traveling from B to A instead of A to B. But that doesn't affect, the correctness of the answer. It informs us of the direction.